Nope. All right. So today we are introducing you to a concept that's hopefully fairly familiar. Function composition. So this is a way of combining functions to get out new functions. We have ways of combining numbers to get out new numbers. We have ways of combining sets to get out new sets. Now we have a way of combining functions to get out new functions. And that's going to be function composition. So if we have three sets A, B, and C, and f is a function from A to B, do you remember what this means? What does it mean for f to be a function from A to B?
You put in A and you get out B of that function, right? Is that right?
Kinda, not quite. A is a set, B is a set.
A is on the left-hand side of your ordered pair.
Yeah, you kind of see this. A is the domain,
B is the image.
all the left-hand elements, and the image is a subset of B. So all the right-hand elements are in B, all the left-hand elements are A. That makes sense?
Okay.
Remember, if it used all of B, then it had a special name. It was what kind of function? On2. And what did it mean for it to be one-to-one?
The inverse is also a function.
The inverse is also a function is one way you can think about it. But that was, well, maybe before we say one-to-one, let's remember what a function is. How do I know when it's a function? I have an ordered pair. How do I know if it's a function? I have a set of ordered pairs, I mean. How do I know it's a function?
Number in the domain that leads to one number in the range.
Right. Every left-hand element is mapped to a unique right-hand element. And it's called one-to-one if every right-hand element is mapped to a unique left-hand element. So f right here, just jumping ahead for a second, it is a function. 1 only goes to one value, 2 only goes to one value, 3 only goes to one value, 4 only goes to one value, 5 only goes to one value. But it's not one-to-one because two different things map to 6. Whereas g over here is one-to-one. So that's what a function was, a one-to-one function and an onto function. And what was a bijection? Both one-to-one and onto. Perfect. Okay, so composition. We have two functions, f from A to B and g from B to C. Now notice something. This thing's image, f's image, is going to be in g's domain. Right? So that's very important when we're talking about composition. So we have f from A to B, and g starts from this same B and then goes to C. Then, that's not R, then g composed with f is one way we read that. Other people like to say g after f. G composed with f is a function from A to C, from this thing's domain to this thing's image, or a subset of this thing's image. Okay? And it's defined by g of f of A is g of f of A. That makes sense?
Yeah.
Sorry, because of how I read this, it comes out the same way because I'm reading the same thing. This and this are the same thing. G composed with f of A is just g of f of A. So let's look at some concrete examples to see this in action. So we'll make A the set 1 through 5, B the set 6 through 9, C the set 10 through 14. And we have f is a function from A to B, here it is, and g is a function from B to C, here it is. What's their composition? What's g composed with f? Well, what does 1 go to? From f, 1 went to 6, and then from g, 6 went to 10, so 1 goes to 10. Let's look at that with pictures down here, and then maybe make sense out of this thing. So f mapped 1 to 6, 2 to 6, 3 to 9, 4, 5. You can see how f maps things. And then here's how g maps things. One way to think about g composed with f is we do the mapping of f, then we do the mapping of g. So when we're doing 1 in g composed with f, 1 goes to 6 goes to 10. So 1 goes to 10. What does 2 go to? 2 goes to 6 goes to 10. Oh, so 2 goes to 10. Where does 3 go to? 3 goes to 9 goes to 13, so 3 goes to 13, etc. That make sense?
Yeah.
So that's one way to think about it. The other way we can think about it is this way. G composed with f of 2, for example, is g of f of 2. What's f of 2?
6.
F of 2 is 6. Ah, so g of 6. Wait, what's g of 6? 10. Ah. That makes sense?
Yeah.
One side note. Notice that the domain of this thing is always going to be the domain of the right-hand function. So if I have function composed with function, all these left-hand elements are going to be the same as the left-hand elements in here. It's kind of obvious when you look at the picture. When we have g composed with f, or g after f, where's our function going to start? It's going to start here and end
F
here.
composed with G.
This is g composed with f.
Saying if it was F composed with G.
Then the arrows would be going, well, we can't do it in this
Saying
case.
then the G left-hand elements would be first.
Uh-huh. Yeah, so it's whatever's on the right-hand side here. The domain of the composition is just the domain of whatever function's on the right-hand side. Whatever function we're doing first. We do the right-hand function first. The innermost function. That make sense? So this is all the tough part. So if it all makes sense here, I think we're good to go from here. But function composition gets people for some reason.
Got me last year. This year makes a lot more sense.
It's a pretty straightforward process, so if it's not clicking, then I'm not explaining it good enough. Sorry, I didn't write what this is. Over here we have G composed with F. So this function is, and it's going straight from A to C. Whereas this went A, B, C. It's just cutting out that middleman. Good?
Mm-hmm.
All right. Let's look at some more concrete examples. So let's look at a function from the integers to the integers, given by f of x equals x squared plus 1. Make sure we understand what this is saying. What's f of 3?
F of 3.
Yeah. 10? You think it's 10?
What?
All right. So now we're looking at this example up here. F is a function from the integers to the integers, given by f of x equals x squared plus 1. What's f of 3? 10? You sure? Yeah, it's just 10. Nice and easy. Don't overthink it. And g, a function from the integers to the integers, given by, what's g of 3? 3. What's f of 1/2?
It's not.
Doesn't make sense. The domain's the integers. Undefined. Doesn't have a mapping. Good?
Yeah.
All right, so we have these two functions. Now let's look at composition. Let's look at g composed with f of 4.
Okay.
So how are we going to think about that? Well, we can use going from this to this to help us think about it. So g of f of 4 is the same thing as g of f of 4. What's f of 4? 17. 16 plus 1, 17. Now g of 17. 2 times 17 is 34, minus 3 is 31. Cool. All right, let's look at it the other way. Let's do f of g of 4. So that's f of g of 4. What do we get when we plug 4 in for g?
5.
We get 5. 8 minus 3 is 5. And then f of 5, plug 5 in for f, we get 25 plus 1 is 26. Notice those are not the same thing. G composed with f is not the same thing as f composed with g. In other words, function composition is not. Anyone know the word for it? Huh?
Inverse.
No.
There's a name for it.
Can you change the order that you multiply?
Oh, it's not commutative.
Commutative. It's not commutative. So it's an operation that's not commutative.
Right.
Multiplication is an operation that is commutative. composition is not commutative. So changing the order that you compose functions makes a huge difference. Now let's do it in general. What's g of f of x? That's the same thing as g of f of x. What is f of x?
F of x is x squared plus 1.
It's just x squared plus 1. What's g of x squared plus 1? That's just 2, x squared plus 1 minus 3.
Right.
And then simplify. That makes sense? Any questions in the algebra that went on here?
Okay, yeah, wait, what? Oh.
Make sense? So, now we have this simplification. This is what g of f of x is. So instead of calculating it this way, we could just plug 4 directly into here. 4 squared is 16 times 2 is 32 minus 1 is 31. Right? Now let's look at g of f of x and make sure this makes sense. F of g of x. F of g of x equals f of g of x equals f of g of x equals f of g of x equals, you might not be able to see that right out around now.
Makes sense, yeah.
That times that is that times that is that, and then you have negative 3 times 2x twice, so you get 12x. And then simplify. And once again, if you plug 4 into this, let's see, 4 squared is 16 times 4 is 64, minus 12 times 4 is 48. 64 minus 48 is 16, plus 10, 26. Same thing. Didn't see that coming. Are you guys just dead?
No, I mean, it just makes
Something
sense.
like
This is
that,
something that
yeah.
we've already learned.
You are dead?
Just teach us.
Just teach you? No point teaching a dead person. That's what concerns me. Yeah, so no point me teaching if you're dead. Let's revive
What are
you.
you gonna do about it?
I don't know. I can throw markers at you. That might do something.
No.
Kick up with something. You go stand outside for a bit? Then
Just
cold, warm you up?
That's
the cold one.
Ah! You thought about that at least. Click it.
You shush.
I can't teach that way. Alright. Let's continue with another proof. So this time we have 4 sets. If A, B, and C and D are sets, and we have F is from A to B, G is from B to C, and H is from C to D, then H composed with G composed with F is the same thing as H composed with G composed with F. In other words, it's associative.
It's associative.
We already said it's not
Yeah,
commutative,
yeah.
but it is associative. You can associate any 2 of those together that you want. You can do it, think about order in like the order you do it, not switching them around.
Right.
Order doesn't matter. So let's prove that these 2 functions are equal. Now, I think this is the first time that we're proving one function is equal to another function. So how do you prove that 2 functions are equal?
Have the same domain and image.
Almost. Just because I have the same domain and image doesn't mean that they're the same function, because they might map differently. Right?
Right.
So you need the same domain, and then they map the elements in the domain the same. Then they're the same function. Does that make sense?
Okay, yeah.
So if they both have their domain 1, 2, 3, 4, 5, and they map 1 the same way, 2 the same way, 3 the same way, 4 the same way, 5 the same way, then they're the same function. So that's what we do when we prove 2 functions are equal. We first prove their domains are the same, and then we show that for any element in the domain, they map them the same. That's how we show 2 functions are equal. That make sense?
Wait a minute. So A and B is equal to A and C.
Sorry.
Maps it the same, doesn't it?
Oh,
Or
you're
are you
saying
saying 2 the same?
you're saying that G composed with F is the same as G composed with F?
Okay, what do you mean by maps the same?
Okay,
Goes to the same number?
yeah. So look, here's two functions that have the same domain. 1, 2, 2, 1. Here's G equals that. Those two functions have the same domain and the same image, but they're not the same function. So how do we check that functions are equal to each other? We check their domains the same. This has 1 and 2 in its domain, good. This has 1 and 2 in its domain, good. That's the first thing we do. Then we say they map each element in the domain the same way. This maps 1 to 2, good. This maps 1 to not 2. So they're not the same. It might seem kind of weird when we're just looking at example, but
Makes perfect sense.
makes perfect sense. Okay, so back to the problem that we're doing. We're proving that H composed with G composed with F is equal to H composed with G composed with F. Right?
Yep.
Okay, so first we need to show that their domains the same. So what is the domain of H composed with G composed with F? Well, remember, the domain of a composition is just the domain of the right-hand function. So the domain of this composition is just the domain of whatever's on the right. In this case, it was G composed with F. You with me? Same thing. What's the domain of G composed with F? Well, that's just the domain of F. And what's the domain of F? That's A.
Wait a minute. Are you missing H?
No.
Yeah, it wasn't.
Okay, come back over here. The domain of G composed with F, the domain of this thing is just A. It's the same thing as the domain of F. So the domain of a composition is just the domain of the right-hand function of that composition. So the domain of this composition, H composed with G of F, is just the domain of that right-hand function, G of F. Same question. What's the domain of G of F? It's the domain of whatever the right-hand function is, F. And then what's the domain of F? It's just A by definition. Good? Alright, similarly, what's the domain of H composed with G of F? It's just the domain of the right-hand function of that composition, which is A. So they have the same domain. Alright, now we need to show for any element in the domain, they map of the same. I just think here, therefore, both the domain is A. Right? Okay, so now this line. So now we need to pick some element out of the domain and show that both functions map it to the same thing. Okay? So let's see how the first function maps it. So H composed with G composed with F of A, how does this map it? That maps it to H of G of F of A, which maps it to H of G of F of A.
Yeah.
Sorry.
Yeah, it's hard to say.
Reading it the same way because it says the same thing, but similarly, let's look at this one. That's not hard, that's H composed with G, composed with F of A, is H composed with G of F of A, is once again H of G of F of A. I don't know. Are you seeing how I'm using the rules there? So it's not.
Rules.
Yeah, I'm just arbitrarily applying those things. I'm using this thinking,
Oh, yeah.
right? So notice how they came out very differently. This was H of this on A. So I applied A to the right-hand thing and then put it all inside H. Notice what I did down here. I applied A to the right-hand thing, F of A, and then passed that whole thing into the left-hand thing.
Right.
So notice how the composition went inside here, but stayed on the outside here.
Yeah.
Okay. As long as you're following that,
It's a little messy, but yeah.
as long as you're following that thinking, I think we're good. Alright, so therefore both functions map A to the same thing. They both mapped it to h of g of f of A. So they have the same domain, and they both mapped each element in the domain to the same thing, therefore the functions are equal.
Therefore, composition is associated.
Therefore composition is associative. Alright. Now we're going to make a special type of function called an identity function. So if you give me a set A, the identity function is a function that just maps each element to itself. Make sense? So let A be a set, then the function, the identity on A, is a set of all ordered pairs, AA, where A is an element of that set. Does that make sense? So just take a set, map every element to itself, now you have the identity function on that set. That's what we mean by an identity function. So notice that for every value in A, the identity on A of A is just A. It maps it to itself.
Yeah.
Okay, wait, what?
Okay. Give me a set A. 1, 2. So if A is equal to 1, 2, then the identity function on A is equal to 1 goes to 1, 2 goes to 2. So if this is A, then the identity on A means this. So if you have some function A, the identity on A equals this. In other words, for all values of A, the identity on A of A is A.
Yep.
The identity on A of little a is little a. Maybe say it that way. Does that make sense now?
Yeah.
Okay, perfect. So, let's do a little proof. Sorry. If A and B are sets where f is a function from A to B, then f composed with the identity function on A is equal to the identity function on B composed with f is equal to f.
Oh. Okay.
Let's prove it. So we need to prove two things. We need to prove that they have the same domain, and then we need to show that for each element in the domain, they map up the same way. That's the way that we show two functions are equal. Or in this case, three functions are equal. Alright, so let's look at their domain. What's the domain of f composed with the identity of A? It's just the domain of the right-hand function, the identity on A. What's the domain of the identity function on A?
A.
It's just A. Where did we lose it?
My body is too tight. You guys will never understand that, but okay. Yeah, I don't know how you did that.
The domain of the composition of two functions
Oh.
is equal to the domain of the right-hand
That's
function.
the function, right, okay.
Yeah, the identity on A is a function. It's a set of ordered pairs
Right.
mapping each element in A to itself. That make sense? Okay. So f composed with the identity on A, take the domain of that. That's just the domain of the identity on A. What's the domain of the identity on A? The function that maps every element in A to A. It's A. Alright, let's look at the next one. The domain of the identity on B composed with f. The domain of the composition is the domain of the right-hand function. What's the domain of f? F is a function from A to B. Ah, it's A. And then finally, what's the domain of f? It's A. So this function, this function, this function all have the same domain.
So wait, identity of B?
Yeah. The function that maps every element in B to B. B is a set, right?
So, IDA and IDB are the same thing.
No,
I mean, with different numbers, but they're the same thing.
they're both identity functions.
Right, but, okay, so is it A, B up there?
Yeah, it's related to these exact sets. IDA is a function that maps everything in here to itself.
Right.
IDB is a function on here that maps everything in here to itself.
Does it make sense?
This
I
is a
thought
set.
A was the domain and B was the range.
Of F.
What?
A and B are sets.
Okay. A is just a set.
Okay.
Okay, let's look at an example over here. F's a function from A to B, right? The identity on A is the function. 1 goes to 1, 2 goes to 2, 3 goes to 3, 4 goes to 4, 5 goes to 5. The identity on B is 6 goes to 6, 7 goes to 7, 8 goes to 8, 9 goes to 9.
Wait, what's A?
In this example, A is right here.
Okay,
B's
and
right
that
here.
is the set that it is.
Yeah, A is this set. The identity on A
And the function is all the ordered pairs.
is mapping each element in A to itself.
Right, the identity.
So we're talking about 3 different functions. We're talking about the function from A to A, the identity function, that maps 1 to 1, 2 to 2 to 3 to 3, 4 to 4, 5 to 5. We're talking about the identity function on B that maps from B to B, 6 goes to 6, 7 goes to 7, 8 goes to 8, and 9 goes to 9. And we're talking about F, which is a function from A to B, which maps 1 to 6, 2 to 6, 3 to 9, 4 to 7, 5 to 7.
We're saying they're all equal.
Yeah, so in this, so let's think about this example over here once again. Let's see what would happen. So here's F. Let's write the identity on A and the identity on B, and let's write out what these things give. So what's the identity on A in this case?
1, 1.
1, 1.
3, 4, 5, 6.
Really goes 5, right? Okay, so there's the identity on A. And now the identity on B. We have 6, 6, 7, 7, 8, 8, 9, 9. Right? Okay, so now let's look at F composed with the identity on A. Here it says. So F composed with the identity on A is equal to, well, let's start with, what does 1 go to?
1. 6. Oh,
Oh, did you see it?
no.
You were right.
Didn't see it.
Okay, so
1. Oh.
maybe we'll write it this way. Let's see what this goes to when you plug in 1. That's equal to F, the identity of A of 1, which is equal to what?
1.
The identity on A maps 1 to what? Okay, so now that's F of 1, which is equal to what? F of 1?
Oh, F of 1, it's up there. Okay, 6.
6.
Right. Okay.
So what happens if we would have plugged 2 in here?
We would have got 6.
And you see how it's just going to keep giving us F? Plug 3 in there. 3 gives us,
No, okay.
the point is,
Hang on, because,
here's the point.
I mean, I see it,
Oh.
but like, how?
F composed with the identity on A of 3 is equal to F of 3.
Right, that makes sense. Is the identity of
Any X you put there, you get X there. No?
Why is it that?
Let's do it in general. F composed with the identity on A of X is equal to F of the identity on A of X, right? You good with this to this? What does the identity function do? It just maps whatever you give it back to
Wait,
itself.
I'm not good with that.
Oh. You are good with that. Okay. And then the identity function, what does it map X to?
X.
Itself. This composed with this of X is equal to F of X. And that's what we're proving.
That seems so self-explanatory almost.
Once it clicks,
It really is, but like, I had it and then I lost it.
and then similarly, and what does the identity on B map f of x to? Just to itself.
Right.
Identity of B, map f of x, that doesn't make any sense.
F of x is just a number.
Right.
What does the identity of B map numbers to?
I have no idea.
If it's 6, it maps it to 6. If it's 7, it maps it to 7. If it's 8,
Right, so
it
the
maps it to 8.
identity maps to itself, okay.
Right. So f of x is just one of these right-hand values.
Left hand.
Right-hand. X is one of the left-hand values. F of x is one of the right-hand values.
Oh, but it doesn't matter because either way works.
Any one of those right-hand values in there.
What? Okay, wait.
It backwards maps to itself.
X is just something out of A. It's just one of these. Right? Let's go back to just using a number.
No, I get that part, yeah.
Oh, okay, you're good with that?
But what about the bottom?
Same thing. X is just something in A, right?
No, it's not. How is it something with A?
Because it's the domain. You plug the domain into the function. Okay, fine. Let's not say something in A. Let's just put numbers here.
So why is it something in B?
Because the domain of this function is A.
What are you talking about? Why am I being so retarded right now?
The domain of the composition of two functions is equal to the domain of the right-hand function, which is A. The domain of the composition of these two functions is equal to the domain of the right-hand function, is A.
But we're not talking about the domain.
Well, when you plug something in, you plug in an element out of the domain, and then you get something out in the image,
Okay.
right? So, when we put 1 there, notice why it has to be. Let's pick something out of B and see how this breaks down. So, what's something in B? 9? Let's plug 9 in there and see what happens. So, the identity on B composed with f of 9. That means we plug 9 in there. What's f of 9?
It doesn't make sense.
Broken. There is no f of 9. Now let's try f of 1. So we plug in 1 there. What's f of 1? 6. Well, I guess we don't really care what f of 1 is. The point is, actually, let's do it. Okay. So then this is equal to the identity on B of 6, which is what? 6. Which is the same thing as f of 1. So this thing on 1 is f of 1. Right? Plugging 1 into this thing and plugging 1 into f directly does the same thing.
Okay.
Another way to think about what this function does. What does it do? It first performs f, which maps 1 to 6, and then maps that element to itself, 6. It's like a little loop right back to itself. That's all it did.
That's the stupidest thing I've ever seen in my life. Okay. Right.
Why?
Like, what's the purpose of that? Why would you want to map it to itself?
The identity function acts with function composition a lot like 1 acts with multiplication. Why would you ever want to multiply a number by 1?
Good question.
Well, you do it all the time when you're manipulating equations.
Like I said, yeah.
You multiply both sides by 1, or you multiply by 1, but you do it in a special way. It helps you manipulate things to see things.
Why are you going to be doing a lot of multiplication by like functions? Are there similar things that you do with functions?
There's a lot you can do with functions. There's a lot you can do with functions. Yeah. I mean, we'll even get to permutations, which are special types of functions. Okay. So, back to our proof. Let's just reset it up. So we have f from A to B. We have f composed with the identity on A, and we have the identity on B composed with f. We're saying all three of those things are equal. First thing we need to prove is they all have the same domain, which is what we already did. All their domains are A. The domain of those two things is the domain of the right-hand thing is A. The domain of those two things is the domain of the right-hand thing is A. And the domain of f is just A. Are any of those confusing?
I think what I'm not getting is the composition part.
Just
The
what?
whole circle. That's what I'm not getting.
They're composed. Well, that's what the whole thing is about.
Son of a gun.
Back to its definition.
What does it mean, though?
G composed
I
with
get
f of
that.
A means
Great,
G
that
of f of
means
A.
nothing.
Does this mean something to you?
That means G of A, right?
That means G of f of A. You're plugging f of A into G.
Right.
So if this makes sense to you, this is just another way of writing that same thing. This is just a more convenient way.
It's not less convenient.
Well, you're seeing it in a very specific context.
G of F. G of F. What does that mean? G of F.
G composed with f,
Yes.
it means when
You
this
don't
is
even
f
know what that
and
means.
this is g, I erased it. It's a function. It's combination. That's like asking what plus
Wait,
means.
G of F equals
G of f,
1 and 10.
it takes this function and this
Right.
function and it combines them together.
Okay.
That's what it does. It gets rid of this b. Here's f, it's one function. Here's g, it's
Right,
another
okay.
function. Now you just do the mapping without and get rid of the b.
Right.
That's g composed with
Okay,
f.
I got that, I remember. Okay.
Okay?
So now, identity of them.
The identity on A is just a function that maps
Identity on
everything in
A
A
of
to
F.
A.
So then it's all those.
One way to think about it
two,
is
three,
do
mix with
one
that.
mapping,
That's all it is.
then do the other. So this means do the mapping of F, then do the mapping of A. F takes all these things and maps it to these things. G takes these things and maps it to these things. I don't know. I'm losing ideas on how else to say it.
Move on.
Well, no, make sure it makes sense.
Makes sense.
It does?
Yeah.
Okay, so using this as F and this is G, what is F of G of, let's give you one, 3.
F. 9. 13.
13!
Woo!
Wonderful. Now let's switch it. What's F composed with G of, pick something that makes sense. Oh, it doesn't work that way. Can't, because we'll get something that you can't map. So yeah, that's all it is. G composed with F of, I'm picking a number here, 1. What does it equal? 10. That's it. That's composition. You're just like doing two functions at once. And that gives us a new function. So now we don't need to talk about doing two functions. We can just get the new function, which is what we did over here. Instead of sitting here always calculating, okay, what's f of 4 and then what's g of f of 4, we can just calculate what the new function is. 2x squared minus 1. So instead of plugging into that function and then plugging into that function, we can go to that function directly. Or instead of plugging into that function and then plugging into that function, we can go to this function directly. That is a composition of f, or of g with f, and that's the composition of f with g, when those are their functions. Good?
Yeah.
And then the identity function just maps each element to itself. So the identity on A maps everything from A to A. The identity on B maps everything from B to B.
I get that part, but how do you freaking do of F?
So this takes everything in A, then maps it to A. Okay, now we've done that one. Then F maps everything in A to B. And now we've done the whole mapping.
So the image of that would be.
Well,
How
so
about you write out those two functions?
write out these two functions. Write out an example of them?
Yeah.
Sure.
So
Right here.
if you know it's 1-to-1, then it
Get rid of that, get rid of that, get rid of that. Alright, let's write them all out. Shouldn't be raised F. So let's see what F does. So, what's it, through 5? And then over here we have, and it mapped, 1 goes to 6, 2 goes to 6, 3 goes to 9, 4 goes to 7, 5 goes to 7. This is F, right? Now let's do F composed with the identity on A. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 6, 7, 8, 9. Here's the identity on A. Here's F. So this whole function is F composed with the identity on A. It is a function.
Always
It maps 1 to 6. It maps 2 to 6. It maps.
So it gives you F.
Yeah!
I'm so confused. What's the point of that?
The whole. That's what you need to see. This part of the function did nothing. From here to here did nothing. And then you just had F. And then the identity on B, what does that do?
It's a very similar thing.
It maps 6 to 6, 7 to 7, 8 to 8, 9 to 9. There's the identity on B. So going from here to here would be the identity on B composed with F. See it? Well, now let's look at the identity on B composed with F. So that's looking at from here over. What does 1 go to? 1 goes to 6, goes to 6. 2 goes to 6, goes to 6. 3 goes to 9, goes to 9. 4 goes to 7, goes to 7. 5 goes to 7, goes to 7. F. So looking at from here to here just gives you F. And looking at from here to here just gives you F.
Well, looking at from there to there.
Right. I wrote it out all in one picture so I didn't have to draw 2 pictures.
Can you do that?
Could you? Yeah, it doesn't change anything, does it?
It is.
Now,
1 to 6.
our function gives us that.
2 to 6.
You're saying, okay, so let's do
Oh.
the identity on B composed with F composed with the identity on A, right?
No, I see.
But our proof already tells us that identity on B composed with F is just F, so that's the same as that. And our proof tells us that that is the same as that, so once again, that's just F. So you're looking at another case of what exactly our proof's talking
Okay.
about.
Okay.
So now you see it all.
Great. Wow, that took me a long time to get that.
No, that's common, that composition, it takes a second for
So weird,
students to
I
finally
saw
get
it.
it.
That's
And then,
Yeah.
so over here, I didn't see any of that.
I know.
That was cool.
For some reason, there's something about it that keeps throwing people off. I'm not sure what it is, because once you see it, it's like, I don't know how else to say it.
Okay.
All right. So, we're proving that that function is equal to that function is equal to that function. They all have the same domain, just A. Okay. So they all have the same domain. Now let's see what they map A to. So F composed with the identity on A of A gives us F of the identity of A on A. The identity on A of A is just A, so it's just F of A, whatever that is. Let's look at this one. The identity on B composed with F of A is the identity of B the identity of B of F of A. The identity on B maps things to themselves. So it just maps F of A to F of A.
Right.
And then F of A is obviously just F of A. So all of them map A to just F of A. Same thing.
Great.
Therefore, all three of those functions are equal.
Does this only work for like the sets like the integers, or can you work with 3 small sets too?
Not once there did we mention the integers. We used them as an example here, but that was just to help you.
Right, but I'm saying, what if F of A isn't in the identity of B?
What if? Oh, why am I looking over there? We're looking over here.
Well, I guess, well, they have the same domain.
Yeah, all that matters is exactly what we stated up here. A, B, and C, those can be complex numbers, or A and B, that can be sets of complex numbers, real numbers. That can not even be numbers. We could be mapping cartoon characters to star ratings. I don't know. It's just a function. Just sets of ordered pairs.
So functions are just kind of like a special type of relation.
Yeah, that's exactly what a function is. It's a special type of relation.
Is it even a special type of relation?
Yes.
Why makes it special? Like it's almost the same thing.
Every left-hand element needs to be mapped to a unique right-hand element.
Right.
And that's what makes it a function instead of just a relation. So yeah, a function is just a relation with that property. Okay, our last proof in this section is actually a homework problem, so don't write it down. I realized it was a homework problem after I did it. Because the author puts there as a proposition, and then when I expect him to like write out the proof, he says it's an exercise. But I just
Is it part of our homework?
I don't know. That's a good question. Maybe I did assign to you guys. So either way, let's go over it. So if f is a function from a to b and it's a bijection, what does that mean?
It's on 2 and
Yeah, it's onto and 1 to 1. So the image of f is all of b, and then f maps everything in A to only one thing in B, and everything in B to only one thing in A.
Alright.
Everything's used once and only once. Everything in the domain is used once and only once, and everything in the image is used once and only once. Make sense?
Not even that, but. Oh, yeah.
Yeah. Okay. So we're trying to show that f composed with its inverse gives us the identity on B, and the inverse composed with f gives us the identity on A.
Okay, that makes sense, I guess.
Yeah, it should kind of make sense in the sense that what does the inverse do? It undoes whatever the function did. So everything gets mapped back to itself. Okay, so let's start by looking at their domains. So the domain of f composed with f inverse is the domain of the right-hand element. What's the domain of f inverse?
B.
All of B?
Yeah.
Yes, all of B, since f is on 2. So that's kind of dangerous. That's not true in general. Just because I have f composed with f inverse does not mean that the domain is all of B. And it happens to be in this case because we know f is on 2.
Right.
Does that make sense? Okay. And let's look at the domain of f inverse composed with f. That's equal to A.
Are you saying on the top one, if it wasn't on 2, then it could be A and B?
Then it's not necessarily all of B. It's only a subset of B. On 2 means it's all of B. That make sense?
Why do they call it
It does?
An onto function means the image is everything over here. not just a subset of over there.
Mm.
You need to go rewatch the lecture.
Yeah.
Probably.
Definitely.
Even though I did homework really easy and it was really fun. So.
Functions are one of those things you deal with in all of math. So this chapter is probably the most important chapter that we cover in this book.
Oh, right. Yeah, I knew that. Onto is when all the numbers are used.
In the right hand column.
In both.
Everything in the domain is always
Always
used.
used. So,
Otherwise it's not
I'm gonna
function.
say that.
Well, just
But
make
yeah,
sure you
and
understand
we
what the
get it.
property onto gives. Okay. So we have the domain of this thing is equal to B. What's the domain of this thing equal to?
B.
The identity on B, its domain is B. So this has the same domain as this thing. So these two functions have the same domain, and these two functions have the same domain. Oh, I write that down. Therefore, the domain on that equals B equals the domain of the identity on B, and the domain on that equals A equals the domain of the identity on
Okay,
A.
hang on.
We're trying to show that that's equal to that, and that's equal to that. I'm kind of doing two proofs at the same time.
Let me ask a question.
Go ahead.
F of F inverse.
F of F inverse.
What's that?
Huh?
Is that just equal F?
No.
What is it equal?
The identity on B.
Oh, it equals, oh.
It's an identity function. It maps everything back to itself. F does something
So
to
it's
it.
like saying
F
one-
inverse gets you back where you started.
1/6 times 6/1 equals 6/6.
No. Well, if you want to think about it that way,
Okay, good, good.
you do have it? Okay. Alright. So we have that the domains are equal. The domain of that's equal to the domain of that, and the domain of that's equal to the domain of that. Now we need to show that they map elements out of their domain the same way. So I'm going to deal with showing this is equal to this first. Okay?
Okay.
Alright. So grab something out of their domain. B. Grab some little b out of their domain. Now since F is 1 to 1,
Wait,
then there has to be some A that maps A to that B.
Okay.
Good? Okay. So let's see what this function maps B to. F of F inverse of B is F of F inverse of B. Since F of A equals B, then F inverse of B equals F of A equals B. And then the identity on B of B is just B. So, this function, right here. Therefore, this function is equal to that function. Now let's show that this function is equal to this function. Grab something out of their domain, A. So grab little a out of A.
Hang on, question. Out of their domain?
Yeah.
Oh.
What's the domain of F composed with F inverse?
Domain of F.
What's the domain of F composed with F inverse?
F inverse. The image of
Domain of F. What? How is that wrong?
What is the domain of F composed with F inverse?
Oh. Sorry, I was listening to it wrong. Yes, domain of F inverse. Beautiful. Equals B.
Equals B.
Awesome.
What's the domain of the identity on B? B. So grab something out of their domain. Let B be something out of their domain.
Cool.
And
So
since
it's assuming that it's true. Oh, no.
no, I'm grabbing some element out of their
Right, okay,
domain
yeah.
and showing they both map in the same way. Good?
Yeah.
Another way, so another way of saying that could be like F composed with F inverse is just the image of F, right?
F composed with F inverse, if it's a bijection, is the identity function on the image. And F inverse composed with F, if the function is a bijection, is just the identity on the domain. You see it? This last group makes perfect sense. Okay, because I'm gonna erase it because I'm pretty sure it's on your homework.
If you have a video playing.
Because I won't put the video until the end of next class.
Why, that is so
Why?
dumb.
Just kidding.
Okay, don't tell.
Don't be angry. All right. So that is function composition. And
Sound good? Okay.
yeah, I'm debating what to
Are we
do.
supposed to do 3 sections today?
No, just two. But the next section's a lot bigger.
Less homework over the break? Sounds good to me.
Yeah, then we only cover one section when you come back.
And then we have
And then do the test right after I cover the section before you can do homework. You can't do that. So I only cover one section next week.
We could do,
No, we would have to do
Or we could do
the
the
test
test.
the same week we do everything.
Maybe we'll just push forward into the next chapter material and then do the test. That's probably what we'll do. So we'll call it there. You can use the rest of class to ask me questions about anything, start your homework, whatever you want. Because I don't know when you guys are leaving. What I heard it was initially supposed to be is 2:30, so.